Hi, my name is John, and today I will be presenting my master thesis, which is matrix multiplication free model for image classification. So let's start with the introduction. So what is really a matrix multiplication free neural network? So the goal of this type of neural network is to completely remove the multiplications from neural networks and just use additions. And the reasons for doing this is that in the chip level, the addition is more simple and uses less energy and lower latency. So if we are able to only use addition and subtraction, potentially we could have the same neural network that uses less energy. So starting from a regular neural network where you have the input and multiply it by the weights and you compute the output. Now, how can we make this without multiplications? So for this, um, what matmul3 does is to replace all the weights with ternary values. So these are -1, 0, and 1. So then you don't need to multiply, and the output is just the input 0 or the input with a minus in front of it. In this way, you don't need to multiply, and you only use addition and subtraction. So this is relevant because we could have AI that uses less power and less money, and also AI could be used for like environments with less resources. The goal of the project is to apply matmul3 to vision model, specifically to image classification. So mainly the goal of the project will be to train a matmul baseline model and then train a matmul3 model and compare both. So let me show you the methods for the project. First of all, the dataset that I use is CIFAR10, which is a dataset for image classification with low resolution images, and it has 10 classes, the one showed in the slide, and it has enough images for training and for validation. Then the model structure that I use is a very simple one, YOLO V1. Um, for image classification, the neural network had around 22 million parameters. And the reason for me for choosing such a simple structure is to really focus on the matmul3 part instead of making the project more complex in this area. All right, so for implementing the matmul model in the GPU, the GPU has tensor cores. The GPU that I was using has 336 tensor cores. And then each tensor core is capable of doing a matrix multiplication and addition operation at the time. So if we do some simple maths and multiply the number of tensor cores times the number of operations that are involved in this matrix multiplication and addition operation, it means that the GPU is capable of doing 172,000 operations per cycle. Yes, like in the tensor cores. So this means that for the matmul matrix multiplication layers, this is very good and it can be used. However, for the matmul3 model, this is bad news because it cannot be used. Uh, Instead, for the matmul multiplication free model, you have to go checking weight by weight if it's 1, 0, or -1 in order to give a output of x, 0, or -x. So this is why for matmul3 models, for inference, it's better to use some application-specific circuits or FPGAs, which are capable of doing the matmul3 operation at once. However, for training, we still use the GPU because it's like very powerful, and for training fast is a very good hardware. So there is a little trick here. When you are training a matmul3 model, in reality, you are training a model with all the weights in floating point representation. But then when you compute the forward pass, you make the model ternary, and by training the model, knowing that there is a quantization, you are able to train the model correctly. So, like an overview, in reality, we are training the matmul3 model in the GPU by using the matrix multiplications, but then the real matrix multiplication free comes in the hardware uh, when the matmul3 model is mapped into the dedicated hardware. So this is when the energy gains come, but the accuracy is the same in both. That being said, now it's time to show the results. So this is a summary table of the best validation accuracies achieved during the project. So for the baseline model, after intensive hyperparameter tuning, the best model achieved around 85% of accuracy. Then I tried to take this baseline and just make it ternary in inference, and this was a complete failure. It was 10% of accuracy, which is just like random chance in a data set with 10 classes. So this shows that the quantization our training is completely necessary. And then for the matmul-free model, there are several phases with several runs each. So here I did some hyperparameter tuning. I also tried with different number of channels. I also tried changing the weight initialization. And finally also try to increase the quantization levels. So instead of doing ternary, I also try with quinary, septenary, nonary weights. And in the end, the best results achieved for the matmul-free gave like a 67% of accuracy. Here we can see the comparison between the best baseline and the best matmul-free. And yeah, we can still see that there are almost 18.5 points of difference between both. If we compare the learning rate schedulers, they are pretty different. The one for the baseline is with lower values, and the one for the best matmul-free is with much higher values and using a cosine scheduler and halving it in the middle of the training process. Then if we look at the average confidence of both models when having a correct or incorrect prediction, we can see that when the model is correct, the value is higher for both. However, for the best matmul-free, we can see that the values are lower comparing it to the baseline. If we look at the confusion matrix from both models, we can see that they follow a little bit like a similar pattern, but the baseline model is less confused. We can see that there is a confusion with cats and dogs for both models, but it's stronger in the matmul-free. And there is also like a confusion between ships and airplanes and trucks and cars, for especially for the matmul-free model. If we look at the weight distribution from both models, here we can see that the baseline is much closer to zero. All the values of the weights are much closer to zero, while for the matmul-free, they are farther away from zero. In orange, we have the matmul-free weight values without being ternarized, and then in red we have the matmul-free values being quantized to not ternarized, because the best matmul-free model was quinary, so it was quantized to 5 values. This way, the main conclusion of the project is that the matmul-free image classification model works and is trainable, but the accuracy is still below the matmul baseline model. In this way, some future work involves keep working on the accuracy and improve it for the matmul-free model, testing different ideas. Then also evaluate the matmul-free model in dedicated hardware and measure the energy. Then also extend from image classification to object detection or other tasks in computer vision, like segmentation or 3D pose estimation. It will also be interesting to adopt more state-of-the-art architectures instead of YOLO one, which is the one used in this project. And finally, use hybrid architectures, mixing matmul-free layers and matmul layers. So this is the end of the presentation. Thank you for listening.